Okay, so this is a demonstration of the Fusion TTA technique using the Fusion Osteotomy Guide distractor. What we have here is the model of a right tibia. The Osteotomy Guide distractor is a reversible or a side changeable instrument. So it would be orientated this way around for a right tibia and flipped over for a left tibia. What we have here is the proximal peg, which anchors and secures the proximal part of the osteotomy guide. And again, this can be applied from either side depending on whether we're operating on a right or a left tibia. In cross section, it's hemi-cylindrical and the flat side faces distally towards the tibia. So the same osteotomy guide is used for 3 different sizes of cuts, which correspond to the different wedge sizes available in the Fusion system. This model is most suited to the 40mm wedge, for which we will set this up using the middle set of holes. So the first thing that we'll do is secure this by holding it in position. Now there's a little top collar on this peg. So if we just hold that in position and tighten up the guide, then that grips the peg very securely. In a clinical case, what we'd be doing now is measuring from the tibial tuberosity here to the proximal start point of our planned osteotomy. We would then make an incision in the fascia there with a scalpel blade and punch through laterally with a blunt instrument such as a mosquito forceps. And that will provide a little soft tissue channel that the peg would slide into, and that soft tissue then would secure the proximal part of the osteotomy guide. Distally, we're going to swing this in to a point where we can anchor the guide distally using a 2.5mm drill bit. Now, the amount of cortex that we preserve is defined by the size of the distal peg that we use, and there are 3 options there, sort of thick, a medium and a thin option. For this plastic bone model, I'm going to use the thinnest option to minimize the risk of fracture. So again, we'll be sliding that proximal peg through the soft tissue tunnel, then swinging this peg in until it comes into contact with the cortex. Now we want to maintain the orientation of the osteotomy guide in the frontal plane. So if the sagittal plane of the limb is orientated parallel to the operating table, clearly this is going to be perpendicular. Then we take our drill with our 2.5mm drill bit. We're going to anchor this as such. Now that drill bit stays in position. In reality, this osteotomy guide would be more secure than it is in the plastic model because proximally the soft tissues will be supporting it. The next part of anchoring the osteotomy, we take a 1.6mm K-wire or Ellis pin. In this situation we're using an Ellis pin because that's what we have available, but it doesn't really matter. And we're going to anchor these in the 2 small holes immediately distal to our peg. Again, that stays in situ. We need to immediately trim that one short. Take another one. Okay, then we place the second pin. Again, we cut that short. The second part is to complete the osteotomy. The next part is to complete the osteotomy. And one of the functions of this proximal pin is to protect the patellar tendon, which will be sitting in this orientation here, from any damage from the oscillating blade of the saw. There may be a tendency for the guide to ride up, so during this part of the procedure it's a good idea just to keep some downward pressure on the guide, and obviously ideally there would be some lavage during this period as well to keep the blade cool. Once the osteotomy is mostly complete, we remove the distal anchorage drill bit. And then we can complete the osteotomy through into that hole. That should be the osteotomy complete now. So the osteotomy guide distractor comes with a Allen key that attaches to the threaded section at the proximal portion, and we can now start to distract the osteotomy and advance it. Once we've advanced it a couple of millimeters, we'll be able to remove that peg. Now again, in a plastic bone model like this, there's a chance of it just falling out, which obviously wouldn't happen in a clinical case when it would be stabilized by soft tissues. Equally, there would be a lot more tension on this, and it'd be more difficult to distract because the bone is stiffer than this plastic, and obviously there'd be the tension from the patellar tendon and the quadriceps as well, which is why the Allen key comes in handy. And it's important sort of to take your time with this part of the process to allow some stress relaxation of the distal cortex there to minimize the risk of fracture. It doesn't matter too much at this stage if the distal part swings away from the cortex. All the force is on these proximal pins. Once you get to a level of distraction which you think is close to the wedge size that you intend to insert, you can just start offering up the wedge to the distractor to make sure that you don't over distract too far. You eventually reach a point where you can sit the wedge in the osteotomy comfortably. Now you'll need to bring your sight line down to below the osteotomy to make sure that the wedge is sitting flush with the medial cortex. And once you're at that point, you can start to back off the tension on the distractor. Now in a clinical case, the tension and the friction is much greater than it is in these plastic bone models. We're going to replicate that to a degree using these point reduction forceps. Okay, and we'll get to a stage when there is no tension on these proximal pins. And we should then be able to lift the osteotomy guide distractor off, so these point reduction forceps are just getting in the way. You might just need to keep adjusting the tension here to make sure there's no tension on those pins. Okay, and that comes out. So we've got a very small fracture in the plastic there. Everything can stay where it is for now. remove that, move it down a little bit further. The next stage is to apply the drill guide to the plate handle as such, and load a 1.5mm drill bit into the drill. Drill through the cranial cortex of the tibial crest. And stop. Replace the drill bit with a 1.6mm Ellis pin. And this Ellis pin goes through the tibial crest, through the hole in the wedge, and eventually through the caudal cortex of the tibia. Obviously you wouldn't be able to visualise that in a clinical case, but you'd have much better tactile feedback from the cortical bone. Drill guide then is removed, and the next stage is to contour the plate. So we'll just need to remove these point reduction forceps for this part. So to contour the plate, we slide it over the Ellis pin or the K-wire, and we identify the point of the first bend. Now you can use a pair of metal instruments, such as a pair of wire twisters or pliers, just to grip and mark where that bend is going to be. And then probably just complete the bend with your fingers to approximately the correct angle. Offer the plate up to the bone in the position so the hole is lined up with the pin. And now we can identify the point of the second part of the contour, just about in this region here. And this part we can sort of complete with your fingers, really. And then it's a case of just ensuring that we have good contouring of the bone, of the plate to the bone. And the principle here is that the plate sits on the cranial cortex, which prevents any cranial rotation of the distal part of the tibial tuberosity. So we'd be pretty happy with that as our contouring. We can cut this pin short now, or we can leave it long. I'm going to leave it long. And the next stage is to load the plate onto the plate holder drill guide. Now the plate is designed with a dynamic tension hole here, very much like a dynamic compression hole in your standard bone plates, and the screw hole is drilled eccentrically, and what that means is when we tighten the screw, it will apply some distal traction on the plate and generate a bit of tension in the pin, so that the whole construct is working like a true tension band wire apparatus. The instrument also holds the plate securely, which basically just makes the process easier for the surgeon. We'll pop that down for a second while we load up a 2mm drill bit into our drill. Okay. Alright, so slide the plate onto the pin. We ensure that the distal hole here is central in the frontal plane, and we can check that by just double checking our drill position. As usual, measure the depth of the screw hole. Okay, and obviously we would normally add 2mm. We're measuring 25mm hole. The longest screw we have available today is the 26mm screw, which will be adequate in this model. These are self-tapping screws. as we tighten the plate, as we tighten the screw, just the final bit of conforming to the bone will occur. And what happens in these plastic models is that the plate tends to sink into the plastic, so we don't get quite as much downward movement, quite as much tension generated as we do in real bone. Okay, but we still end up with a fairly secure construct. So finally, we remove these pins. Now, if you use a smooth pin, these will remove very easily with a pair of pliers. Cut the pin to approximately 8 to 10 millimeters. The pin is then bent medially. And then twisted into position so it sits snugly just against the medial cortex. And that's the completed fusion TTA.